Accept చేసారా ఆడియో ఉందా సరిగా
this handler just trying to get some information about this handler. Handler stands for
Hello, good morning. This is Professor Anjaneyulu from NIT. Can you hear me, please? Hello.
Yes, yes, sir.
Yes, sir. Yes, sir.
Is my video and audio are clear, please?
Yes, sir.
Yeah. I'll just start sharing my screen. Just tell me if an issue, please. Yeah. Is my screen visible?
Yes, sir. Yes, sir. Your screen are visible, sir.
Yeah.
Sir, just to off the screen share, because we are a small screen sharing is there about your that introduction. So after that you can share, sir.
Yeah. So shall I just keep it like this?
Okay, sir.
Yeah. Thank you.
Okay, sir. Thank you.
Thank you. Yeah.
Usha ma'am. Usha madam.
Yes, I am ready.
Sir, madam, you start, madam.
Okay, sir. Good morning, speaker, Dr. Anjaneyulu, participants, and my dear faculty friends. On behalf of Vignan's Institute of Management and Technology for Women, I welcome you all to the second day faculty development program on Microstrip Antenna. I am Usha Rani, working as an assistant professor in EC department. It's my great pleasure and honor to introduce today's speaker, Dr. Anjaneyulu, who has obtained his PhD in radar signal processing and currently working as professor, head of the department, Electronics and Communication Engineering, National Institute of Technology, Warangal. He has 23 plus years of teaching experience. His research focus is on microwave engineering, radar engineering, antennas and propagation, computer networks, and artificial neural networks. He has successfully completed 3 funding projects. One is higher order spectral analysis techniques for identification of low probability of intercept radar signals, a funding project of DRDL, DRDO, and development of adaptive digital beam forming algorithms and analysis for active phase array radar of DRDO Bangalore, and the third one, virtual reality based simulation for electronic window from Ministry of Mining, Nagpur. And is presently working on two of the research and development funding projects. He so far guided 2 research scholars, leading to the award of PhD, and 2 of his research scholars have already submitted the synopsis, and 3 of the research scholars are currently pursuing under his guidance. He so far guided 45 BTech projects and 40 MTech projects. He has published 26 research papers in national and international journals, and also published 27 papers in national and international conferences. Coming to the workshops and conferences Sir conducted, he was the resource person for 7 of the workshops and conferences, and course coordinator of 15 workshops and conferences, and participated in 30 of the workshops and conferences. His achievements have been recognized by different awards, including Best Paper Award by IEEE Malaysia Conference and Best Paper Award by IEEE Journal Gold Medal Award. He also visited University of Malaysia 2 times for presenting paper in IEEE International Conference, and also visited University of Khalifa University, Abu Dhabi, UAE. He is also a reviewer of Defense Science Journal, DRDO, New Delhi. It's impossible to mention is every single accomplishment because they are a lot. Last but not the least, I just want to introduce myself to Dr. Anjaneyulu sir. as I am one of his students of 1997 batch in NIT-Warangal, and he taught me computer organization, and he was my BTech project guide. Thank you, sir, for everything what you have done for me. And now I request Dr. Anjaneyulu sir to take over the session.
Good. Thank you. Thank you for the introduction.
Good morning, sir. I'm your student.
Oh,
1997 FDP, sir. Yeah, yes, sir.
I see. Nice, nice.
And you were my project, sir, and I spent most of my time in your cabin, sir.
Oh, great.
Yeah.
What's your project that time? What was the topic?
Sir, I don't surely remember it.
Okay.
It's already 20 years back, sir. It is 21, sir. In
Okay.
2001, sir.
Oh, 2001. Okay.
Yeah, in 2001.
Oh, nice, nice. So, after 20 years.
Yeah, after 20 years, sir.
Okay, thank you.
Thank you very much.
Yeah. So, yeah, is my screen visible? Yeah. Shall I start? Hello?
Sir, screen is not visible.
Not visible?
No, sir. It's not visible, sir.
Okay. All right. All right. Okay. Okay. So now it should be okay.
Yeah, yes, sir. Now it's visible.
Okay. Thank you.
Thank you very much.
Okay. Good morning, everyone. The participants of this FDP and the course coordinators and Dr. Samiran and the other management principal of Vignan Institute for Women. Thank you for inviting me to present a talk on reconfigurable microstrip antenna as part of the FDP that you are conducting. I hope the participants are mostly the faculty working in various engineering colleges.
Yes, sir.
And maybe the PG students who would like to have exposure for this area of microstrip antennas. So the beneficiary of this talk will be the PG students who are into this area and also the faculty who are pursuing their research work in this area of high frequency engineering of antennas, and also who would like to understand what is all this about, and then probably they would like to pursue their research in this direction. But that's how I modulate my talk on this. To start with, maybe I'll give a few basics of microstrip antennas, and maybe try to see that it's not much of overlap from what you already been taught yesterday or you discussed yesterday's first session. Okay. So today, as we see that we have much complex circuitry that are into the market, and why we need reconfigurable antennas. So as you see. Yeah, I think I was muted. I hope I am clearly audible now. Yes. So as you see here, that we have an example of a 4G smartphone that I'm showing on the screen. Generally, as you see that the kind of facilities that we have on this particular phone for various applications that we see, starting from simple GPS application. We have a Bluetooth application, then fourth generation application, 5G anyway on the way, and GSM application. So as you see here, we have different antennas for GPS, one antenna, for Bluetooth, one antenna, and for GSM, one antenna. So we have basically different antennas working in different frequency ranges. Now, as you see here, GSM is GSM 900, 880 to 960 megahertz band. and UMT 2000 3Gs and 25 to 2055 megahertz. So we have different antennas mounted in this particular gadget called a smartphone for various applications. So do we really need to have such an arrangement of various antennas? Can we not have, an antenna which can, reconfigure itself for all these applications instead of having multiple antennas? So the system complexity will be more, design complexity, and then board complexity, and then the software hardware complexity will be more. If there is a facility that we have an antenna, typically maybe called as per the English meaning, which actually changes its characteristics as per the user's application on demand. Okay, that would be nice. So this is a motivation for the concept of working on what is called a reconfigurable antenna, which can be reconfigured through commands of the software or a combination of hardware and software, which changes its electromagnetic characteristics to act for different application, but a single antenna. Okay, so okay, yeah. So therefore, as you see here, we have all these applications: Wi-Fi, WiMAX, 3G, and UWB, and TV, direct video broadcasting, GPS, and 60 gigahertz application, and Bluetooth. Okay. So for all this, we can, just imagine that, same thing you would like to have on a laptop. We typically imagine, different antennas as we see in this figure rotating out of the device. Okay. But is it really required? Can we not have a single antenna instead of several such antennas? Okay. So if you see here, what is the need for a multifunctional antenna? So this is another name, a simple name for a reconfigurable antenna. Reconfigurable is a more technically, sounding word, but multifunction is a generic English word that antenna can work for multiple functions. So at present, there is an increasing demand for several wireless applications. As you see here, once again, I am showing the different frequency bands and their, IEEE notation of various applications. For example, Wi-Fi 802.11b GN, typically from 2.4 to 2.48 gigahertz, and antennas may be 3x3 MIMO configuration, and WiMAX. Okay, WiMAX 802.16, these frequencies, and then maybe a diversity implemented. Similarly, 3G, again, different bands are there. And then Bluetooth, Bluetooth, we have IEEE 802.15, GPS, UWB. Okay, so it means to say that the multifunctional antenna that we are trying to understand now should be able to operate in all these frequencies with a software control. Or whenever user switches from Wi-Fi to GPS, the antenna should be able to switch from Wi-Fi frequency band to Bluetooth band, like that, and so on and so forth. Okay. So therefore, to have this one multifunctional antenna for catering for the needs of the user, the solution is what is called a reconfigurable antenna. Okay, this is a motivation. Okay, then as you see that we have different types of antennas. Again, I'll be spending about 5 to 10 minutes of my time on showing different antennas. As you see here, that these are the different variants of planar antennas, okay, of category under microstrip antennas, which are basically lightweight and smaller in dimension, easy for manufacturing, easy integration. So some of these concepts probably yesterday in your introductory lecture you would have seen, but so therefore I will not spend more time. I just quickly go through all this. Okay, so starting with the first model by Deschamps in 1950s, the microstrip antenna started with various configurations. So the kind of propagation that we see is a quasi TEM, and we use the radiating patches molded or hatched onto the basic substrate material. So which allows a kind of a quasi-TM wave to get established between the ground plane and the radiating patch through the dielectric material. Anyway, I will not go into the radiation mechanism and field theory of how this happens. I think this you would have already learned or you'll be going to learn anyway. These are some of the pros and cons of microstrip antennas compared to other category of antenna. Because microstrip antennas being low profile and less weight, they are most suitable for gadgets like smartphones, etc. That's the reason why we are trying to understand more about these microstrip antennas. So they are basically, as I said already, low profile, low weight, low price, easy integration, and batch production. These are the pros. And then cons, narrow bandwidth is one, low efficiency is one, spurious field radiation, okay, and a limited power handling capability because it's a very small, device, and poor scan performance. Okay, these are the disadvantages or cons. But however, we do have techniques to overcome all of these, limitations. There are good techniques by which we can improve all of them. It's a general a device. I'm showing you a photograph of a base station, typical base station of a communication system, which contains receiver circuitry. Where this is the practical photograph that I'm showing how these things are integrated. So the antenna goes somewhere here with all other elements, okay, which may be occupying a size of typically 4 centimeters by 2 centimeters, okay, which has a low noise amplifier and a power distributor and filters, diplexers, so on and so forth. So whenever we are trying to understand about antennas, finally we have this kind of visualization in our mind, so that ultimately they are going to be integrated into a device, like this. And we can also have these antennas not just as independent antenna. We can also organize them as arrays. Okay, so we can have a linear array of microstrip antenna, which will have several radiating elements or patches. We can have a 2x2 array or 8x2 array or 4x8 array for different applications. So therefore, microstrip antenna need not be having always a single radiating patch or radiating element, but you can have any of these configurations depending on for what kind of application that you are trying to deploy this antenna, and with different types of feeding mechanism. Okay, so anyway, I will not go into more details of this, but just a brief introduction to you that these are the various types of microstrip antenna that we are trying to understand. And we'll be using these antennas in various applications, starting from aircraft and ship antennas for communication and navigation, and we use them into missiles because of inherent advantage that we have. Because of lightweight is one, and then in fact we can integrate the antenna into the missile body itself. Okay, we can have a cylindrical antenna because missile is typically of cylindrical shape. We can have the microstrip antenna bent around the body, and then it is possible to have. They are actually called conformal antennas, which conform to the surface of the object on which we are trying to mount. Similarly, we use for satellite communications, mobile radio, as I told you, remote sensing, biomedical, and various other applications. We use these antennas. So, and these antennas, while generally we have a patch which actually radiates, but it has to be fed through through some source. Okay, so there are different ways by which actually we feed the radiating element or a radiating patch. So these are the various feeding techniques that we use. Like inset feed and fed by quarter wave transmission line, coaxial probe feed, and then coplanar microstrip feed, gap coupled feed, proximity coupled microstrip feed, aperture coupled microstrip feed, coplanar waveguide. These are the different mechanisms by which we feed the radiating patch. The radiating patch can have, again, it need not be rectangular always. It can be in circular shape. It can be any other shape that you design for a given application, and it may have various other things as well, like you may have slots in the patch, and you may have different different parts of the patch can be combined together depending on the application. But however, that there should be a kind of a mechanism through which you feed this radiating part of the antenna. So these are the methods as I've shown here to feed the antenna, but each and every feeding technique has its own advantages. Like for example, wherever you want, wherever you want to have a better reliability, as it is shown here, we can go for a microstrip feed. Similarly, wherever you want easy impedance matching, we can go for coaxial feed. So like that, each and every one has its own thing. For example, for a proximity feed, the resonant frequency is the highest. Okay, so I have shown here a few of the feeding techniques that I have shown in the previous screen with respect to their respective advantages and characteristics in terms of return loss, resonant frequency, VSWR, and then spurious radiation, and then polarization purity, ease of fabrication, reliability, impedance matching, bandwidth, etc., etc. So as you see here, if at all you want to have more bandwidth, we must go for aperture feed, as it has got 21% bandwidth. Okay, so like that, we have to choose an appropriate feeding technique. So after a complete discussion on the microstrip reconfigurable antennas, if there is a time for us still left before 12 o'clock, and if time permits, maybe I'll spend little more time on showing you the advantages and then various mechanisms by which it works about all these feeding techniques. But at present, I just leave it at this stage. That hello, sorry. Okay, I don't know. My mic is being muted by someone, maybe by accident. Okay, all right. So yeah, so let me go ahead. I'll go ahead now. Yeah. So this is one specific, feeding technique. Maybe I'll spend a little more time here because this is a popular feeding mechanism used in reconfigurable antennas. So coplanar waveguide, invented by C.P. Venn in 1969, okay, which allows quasi-TEM wave propagation. So as you see here, so we will have parallel strips of the material, copper material, which actually acts as a feeding mechanism. As is shown in one of the photographs here, that this is the coplanar waveguide feeding mechanism, and this part is the radiating part. Similarly, as you see in this photograph here, so this is the feeding mechanism, and this is called coplanar waveguide feeding mechanism, where we see three parallel metal strips, okay, and we'll have a connector connected here, and through which actually we feed the radiating patch. So this is the very popular mechanism, feeding mechanism, that we use for reconfigurable antenna. That's why I'm spending a little more time here. So as you see here, some of the photographs here. In fact, these photographs, some of them are done by my own research scholar, and whose work actually I'm going to present now. She has worked on reconfigurable antennas. So I'm going to present all the research work details of my student in this presentation of different types of reconfigurable antennas. Okay, so we can connect or we can mount the connectors as shown in this particular photograph. Yeah, and when you especially come to what are the pros and cons of this particular feeding mechanism called coplanar, waveguide feeding mechanism, these are the advantages: easy fabrication, easy surface mounting. That means whenever you want to attach connectors, different connectors onto the feeding line, easy to fabricate and easy to solder those lines. And then we can achieve larger bandwidths and eliminates via holes through the board, and low radiation loss. It has low radiation loss because the strips are a bit narrow, and low profile, low weight already there. I mean, the green ones are in general are the advantages of all microstrip antennas. The yellow ones that are shown here are specific to the CPW feed, and then the top two are from the fabrication point of view. And the two disadvantages mainly to be handled and for a careful design are high frequency losses and mode coupling. But anyway, as I told you earlier, we do have some techniques to avoid or to minimize these two limitations. Yeah. Now, when you compare the microstrip feed and the CPW feed, these are the comparisons. See, microstrip feed will have only one particular feed line, and coplanar waveguide will have 3 parallel strips that we see here. The middle one is actually the feeding line. The side ones are part of the ground plane. They are part of the ground plane on one side of the patch. So if you just compare the microstrip and CPW, because microstrip is also one of the popular feeding mechanisms, CPW has coplanar waveguide has its own advantages, which is also popular now. If you just compare here, microstrip has low bandwidth and coplanar has a large bandwidth, and microstrip may need via holes, but this eliminates the need for via holes. High radiation loss here, but here low radiation loss. Here spurious radiation is there and a negligible feed radiation. So this is due to the mechanism, as you see in these two pictures here. The first one, this is actually a simple microstrip feed where I have got a single feeding line and I have a ground plane here, and then this feed line connects to a radiating patch. So this is the kind of a field distribution that you see here. Whereas in CPW, as you see here, the center one is a main feeding line, okay, and the side ones are actually part of the ground plane, okay. So therefore here the coupling mechanism and also the electric and magnetic field line distribution is in such a way that the feed radiation is negligible here. So therefore we have a low radiation loss here and possible to have better bandwidth. So that's a basic comparison between a microstrip feed and a CPW feed. And CPW feed, as I said earlier, it is more popular in reconfigurable antennas. And that's the reason why I'm trying to spend a little more time on this particular aspect. Yeah. Now, coming to the reconfigurable antennas. Okay. The basic definition is now can intentionally and reversibly change the distribution or character of their performance governing electromagnetic fields are said to be reconfigurable. I'm actually reading the sentence as it is because all these words are important. Antennas that can intentionally and reversibly change the distribution are characteristics of the electromagnetic fields. They're said to be reconfigured. Intentionally means we should be able to change. The advantages, again, as we earlier discussed, lightweight, smaller in dimension and lower price, and it combines multiple antenna functions into a single antenna system. So this is the basic understanding what reconfigurable antenna means. So far so good. Is it okay? Can someone give a feedback, please?
Yes, sir.
Yes, sir. Yes,
Thank you.
Yes, sir.
So now these are the different types of reconfigurable antennas, as you see here. Basically, the way in which we implement reconfiguration mechanism. Okay, since we said in the previous slide that we should be able to intentionally change the radiation characteristics and also change the frequency bands. So therefore, how do we achieve it? So these are the ways in which we can achieve. And in terms of these are the electromagnetic characteristics, means we can change the pattern of the antenna, so it comes under pattern diversity, and we can change the polarization of the antenna system called polarization diversity, and then we changed depending on the application called frequency diversity, and we can combine all this. We can change pattern, polarization, and frequency simultaneously depending on our interest. That is called compound reconfigurable antenna. Okay, so based on the nature of radiation characteristics, these are the types. And now, if at all you want to, have a pattern diversity, it means we can change the direction of radiation. That means antenna radiation pattern, and we can have variation in the gain, and we can also have variation in the beam shape whenever we talk about pattern diversity reconfigurable antenna. Similarly, when you say polarization diversity, it means we can change from left circular to right circular polarization, or we can have linear polarization. Okay, so circular to linear, linear to circular also can be changed. So that's what we mean by reconfiguring the polarization. Yes, that's called polarization diversity reconfigurable antenna. Similarly, when you talk about frequency diversity, we can have switch tunable, means we change from one band to another band, switching, or we can continuously also vary. It's called continuous tunable, using varactors and using what are called PN diodes. And compound reconfigurable antenna means, again, as I told you, combination of all the above, all the three. Okay, so for achieving those reconfiguration mechanisms, as shown in the previous slide, so we can have pattern, polarization, frequency, or a combination of all this or some of this. To achieve this, what kind of mechanism we can use? These are the various mechanisms. We can have electronic way of reconfiguring. We can have optical way of reconfiguring. We can have electrical/magnetic way of reconfiguration, or we can have mechanical or electromechanical. Okay. So under electronic, we can use devices called PIN diodes. Okay. PIN diodes to be mounted onto the antenna, so that electronically we can change the configuration. Okay, frequency to polarization or polarization to pattern, whatever. We use PIN diodes, means electronically we make the diodes on and off. Okay, so that the radiation characteristics of the antenna change. Similarly, varactor diodes can be used. FETs also can be used. So this comes under electronic way of reconfiguring the antenna characteristics. And the other one is optical. Here we have to use photosensitive layers, a bit of complex mechanism. Similarly, electromagnetic. So we use ferroelectric materials or components, ferrites, liquid crystals. These mechanisms we can use under electromagnetic way of reconfiguring. Similarly, electromechanical, we use the microelectronic, mechanical switches called MEMS. Okay, to have this way of reconfiguration. So we understood now the meaning of a reconfigurable antenna, and we also understood what radiation characteristics can be reconfigured, and we also have seen in this slide what are the ways and means by which we can achieve such reconfiguration. Okay. All right, so these are some of the photographs of how reconfigurable antennas look like. For example, as you see here in this figure, yes, as you see here, this is a reconfigurable antenna. So there are actually, as you see, there are some diodes, tiny diodes are there, and you see the two yellow wires. The two yellow wires actually are nothing but DC power supply to these diodes to make them forward and reverse biased. Okay, that means we switch off or switch on the diodes through this DC lines. Okay, so when you switch on and switch off the diodes, their characteristics vary. That's the meaning. So as you see in this diagram here, I have a circular, antenna here, a circular patch essentially consisting of several elements here. Okay, and the black ones that you see here are nothing but diodes, tiny diodes that you see here. So when you make them on and off, it connects different sections of the antenna, connects or disconnects different sections of the antenna so that their radiation characteristics vary. Okay, again in this photograph, as you see here, several wires that we are seeing. In addition to the RF connector, you are seeing some wires here. Okay, so those wires form what is called a DC bias network. Okay, so this DC bias need to be fed to the diodes so that they can be made on and off. Okay, so this mechanism of making on and off is actually called reconfiguration mechanism using PIN diodes. Okay, like that. See, even this photograph shows, a kind of an antenna here. So I'll show you some examples now. which are some papers which are published. For example, this is one. Yeah, I mean, this is actually. Yeah. Okay, fine. So, so when you make for the previous antenna that you see here, these photographs I have shown you. So, depending on, as you see here, it is using 3 switches. A particular antenna that I have shown in the previous diagram using 3 switches. The first one, it's published in IEEE, one of the papers that I am showing you. As you see here, mode 1 means what, diode, since there are 3 diodes, D1 is on, D2 is on, D3 is also on. Okay, it is red color. So therefore we get this kind of radiation characteristics. Means what? The frequency of resonance is around 2.5 gigahertz. Okay, so therefore the antenna operates when you switch on all the 3 diodes. Okay, it resonates at 2.5 gigahertz. That's what actually it is showing here, resonant frequency. But when you make D1 on, D2 on, but D3 off, okay, this is called state 2 or mode 2. It is a blue dashed line. That means this one. So the frequency has now changed from F1, which is nearly 2.5, to F2 nearly, which is 3 gigahertz. Okay, so this is what we mean by reconfiguration. So now the same antenna, okay, structure like what you have seen in the previous diagram. When you make these diodes which are mounted on the antenna to on and off by different combinations like what is shown here, their resonant frequency is changing. It means that the antenna is operating in different frequency bands. Okay, so therefore that is called frequency reconfigurable antenna. Okay, so if you are aiming at designing a frequency reconfigurable antenna, it means that you should work out with some structure that I have shown in the previous slide and get characteristics like this. So this is actually a return loss characteristic of an antenna. You should get a characteristic like this, where you have to show that by operating the diodes at different modes, you are getting the resonant frequency differently. It means it is a frequency reconfigurable antenna. That's the meaning. Okay, so this is how we should actually understand and then accordingly design. This is one example of a reconfigurable antenna, and this is another example. Okay, so as you see here, the structure is, you see, there is a a T-shaped antenna, and as you see here, so as you see here, this is a CPW feed, because I have a line here. The center line is feeding this this patch. So this is radiating actually. The other part that you see around it, the black one, is the ground plane. Okay, so we will have the radiating patch and the ground plane on the same side of the antenna. Conventionally, for patch antennas, as you have learned from yesterday's beginning introductory session, that we have the ground plane at the bottom and radiating patch on top. Okay, but when you are implementing using a CPW coplanar waveguide feed, the ground plane and radiating patch are on the same side. So bottom will not have any ground plane, no ground plane. Ground plane is also on the same side. So the black portion that you see is a ground plane. So therefore, between the two ground regions here, I have a line here. So this combination is called CPW feed. Fine. Okay. Now again, as you see in this diagram, there are two elements here. What you see here, they are diodes actually. Okay, this is one diode and this is another diode. Okay, so what we are trying to do here, that when this diode is on, it means there is going to be another short circuit between this place and this place. Similarly here, when it is made on, okay, so therefore as you see here, this antenna, this is actually called a folder slot antenna using 2-pin diode switches. Okay, the frequency switched from 5.14 gigahertz to 5.75 gigahertz. So it's a frequency reconfigurable antenna operating at 2 frequencies using 2 diodes. So as you see in this diagram here, bottom diagram, it is your return loss S11 versus frequency. So the solid line is measured with the diodes off. Diodes off means there is an open circuit between this region and this region. Okay, All right. Whereas the diodes off, and then with the diodes on, we see this gray solid line. So when the diodes are off, the frequency is around 5.14 gigahertz, as you see here. But when the diodes are on, the frequency is switched to 5.75 gigahertz. Okay. So this is the design of what is called. This is one example of the design that I am showing you, called frequency reconfigurable antenna, and this they have designed for what is called wireless LAN, WLAN application. Okay, WLAN. This is actually 802.11a standard at 5 gigahertz. 802.11a is 5 and 802.11b is 2.4 gigahertz standard. Okay, so these people have designed a reconfigurable antenna for wireless LAN application with two frequencies switching. Okay, 5.14 to 5.75 using two diodes on this. Okay, so this is another example of a frequency reconfigurable antenna. Fine. So like that, I'm showing you different examples. This one is actually a polarization reconfigurable antenna. As you see here, this is a polarization reconfigurable antenna. So this shows, you see, polarization reconfigurable antenna. This is a paper, and it says dual band polarization antenna for wireless LAN application. Okay, as you see here, it is actually 2.4 and 5.8. Both they have achieved here, and polarization switched between horizontal, vertical, or 45 degrees linear polarization. This is what they achieved here. Okay, vertical polarization, horizontal polarization, or inclined 45 degrees linear polarization, where the electric field vector is 45 degrees with respect to. So you see here, state one is they are using two diodes here. Okay, it uses two diodes. Let me check. Is there a diagram? Okay, diagram is not there here. Maybe I'll show. Anyway, the bottom diagram is a different application. So they are using two diodes here. When both diodes, one is on and one is off, we are getting horizontal polarization, and this is on. That is both are this is off and this is on. We are getting vertical polarization, and both are off. We are getting 45 degree oriented thing. So this is called polarization reconfigurable antenna. Again, they are using two PIN diodes to switch the configuration or to switch the frequency from 2.4 to 5.8. Okay, so polarization, I mean, they have done it at two different frequencies. Okay, and three different polarization they are getting. And the bottom one is another example, okay, of a reconfigurable antenna. It is called symmetrical reconfigurable multi-polarization circular patch antenna. Symmetrical reconfigurable and multi-polarization. So in this example, they have achieved 2.4 gigahertz. That means wireless LAN application, circular patch antenna, which uses 12 diodes. Yes, you see here, this configuration, they are using 12 diodes because they have got not 12 different sections. Okay, as you see here, these are the sector shaped 12 different sections are there, and these sections are connected to the central circular patch. Okay, it's a wheel shaped antenna, and there are 12 sections connected to the central portion with 12 diodes. That the red ones that you see here, the tiny red ones, are nothing but diodes which can be made on and off. Okay, so a 2.4 gigahertz circular patch antenna which uses 12 diodes, and it able to generate 6 linear polarization at 30 degrees interval. Okay, it means 0 degrees, 30 degrees, 60 degrees, 90 degrees, again 120 degrees, 150 degrees, like that. Okay, that's why they are called as multi-polarization circular patch, circularly shaped patch antenna, but different polarizations. 6 polarization they are able to generate. So this is another example of a polarization reconfiguration. So far I have covered examples of linear polarization, sorry, frequency reconfigurable examples, 1 or 2 I have shown you, and polarization example just now I have shown you. Okay, and this one is an example of a pattern reconfigurable. Okay, how the pattern changes. All right. So as you see in the diagram here, okay, again there are 2 examples that I am showing you here. The pattern now, One is in state 1. Okay, they are using 8-pin PAN diodes connecting the edges of the square patch, reconfigures the pattern from bore side to conical. Okay, so in state 1, that means when some diodes are on, some are off. It's a bore side pattern along the bore side axis of the antenna, and it becomes conical pattern when the two groups of diodes are forward and reverse biased. Similarly, conical pattern with maximum power level in the ZX plane and maximum power level in ZY plane. Okay, so therefore it is also changing the planes. So this particular antenna, they use a pattern reconfigurable U-slot antenna, and its application in MIMO. Okay, that's how they named it. These authors who actually fabricated this antenna. Similarly, the bottom figure shows another pattern reconfigurable antenna, circular antenna, but ultra wideband monopole antenna for ultra wideband applications. Ultra wideband is actually starting from 3 GHz up to 10 GHz. As you see here, the pattern is different in the 3 figures. As you see here, the pattern is different. One has 4 lobes, other one has 2 lobes here. This one also has two lobes. Okay, so this is an example of a pattern reconfigurable antenna. Similarly, this is another example of a pattern reconfigurable antenna. You see here, this is another example. So this is an antenna structure. This is again a pattern reconfigurable antenna. Now what they have here, they have a square patch in the center, and then at the edges they have C-shaped patches. Okay, and then the blue ones are nothing but diodes here. Okay, there are 4 diodes here. Okay, so this particular antenna is a pattern reconfigurable antenna to work at the Ka band frequency. Okay, Ka band is actually your 27 to 41 GHz application. Okay, so as you see here, the 3-dimensional picture of a pattern, its direction is changing actually. So therefore, this is one configuration where this particular diode is on, the remaining are off. Whereas here, this is on, remaining 3 are off. So like that, they have 4 combinations now here. Okay, so this is an example of a pattern reconfigurable antenna. So this is another complex example of again pattern diversity. Okay, for digital TV applications. Okay, this is another one. Here you have 2 L-shaped slots. Okay, and this antenna is a reconfigurable circularly polarized microstrip antenna with a slotted ground plane. Okay, so we have got 2 L-shaped slots are located on the back plane, and so therefore diodes which connect and disconnect. Now, as you see in this figure, they have used 7 diodes D1 to D7. Okay, which actually connects and disconnects different parts of the different copper regions of the antenna. So we have different. This is the feeding mechanism. Okay, right. These are a bit different feeding mechanism that they have used. And this is another example of antenna. Okay, single feed polarization reconfigurable antenna. Okay, coaxial feed they have used here, and they have used now 4 PAN diodes. Okay, so to reconfigure from right-hand circular polarization to left-hand circular polarization. Okay, so this is actually a polarization reconfigurable antenna. Okay, similarly, we can have examples for radio frequency identification applications and so on and so forth. Now, actually, I will show you the design of some of the reconfigurable antennas that we did. So whatever I am showing from here onwards, nothing but the research outcome of one of my research scholars at NIT-Warangal. All these examples. So I will show you some more details of our research work for all these different types of reconfigurable antennas. Now, the first application that I am showing here is a compact CPW fed patch antenna for 5.8 GHz RFID application. This is not reconfigurable antenna, a normal antenna. Okay, just to start with an example I am showing you. Though it is though it's not reconfigurable, but I'll show you the reconfigurable mechanism after this. Okay, a symbol antenna. So this is having a H-shaped patch Now, as you see here, this is a H-shaped patch. That is the main radiating element. And the feeding that you see here is a coplanar feed because I have got ground plane here and ground plane here. And the center line is actually through which we feed the H-shaped radiating antenna. And these are the various dimensions of this particular antenna. And this is designed for RFID application at 5.8 gigahertz. Okay. So as you see here, this is the parametric analysis. I think you are going to learn now as part of your hands-on. I think you have hands-on as part of your FDP. Maybe you'll be using one of the simulation softwares like HFSS or IE3D, okay, or FICO, or Microwave Studio. I don't know which is included in your FDP, but most probably you'll be exposed to one of these high-frequency simulation software packages through which you can simulate these antennas and later on fabricate on the things. So as you see here, they have used in this antenna we have used FR4 as a substrate, 504 FR4, and the height of the substrate. I mean, here it's actually a parametric study, okay, and when the height between the ground plane and the radiating patch, when it is varied, how the frequency changes, how the return loss changes, and how the bandwidth changes. So once you do this parametric analysis in the simulation with the dimensions mentioned here, okay, so we have to now optimize the dimensions accordingly. Okay. Now here at 1.2, even though we have changed the height in simulation, but practically we have to check whether with a thickness of 1 mm is available, the substrate is available in the market or not. Okay. So we have now identified 1.2 mm substrate is available. So therefore, this particular height is chosen for fabrication. Okay. And let us say if 2.0 is also available, we can take this particular thing, fine, at 5.3 gigahertz. Okay. So similarly, because we wanted 5.8 gigahertz here, so 5.77 is nearly, or 5.79, though it is nearly, but we don't have 1 mm thickness substrate, so we have chosen 1.2, which is nearly to this. So at 5.77 that is chosen here, the epsilon r is 4.4. Again, we have to make this combination at this frequency. So whenever we are choosing a substrate, we have to choose in such a way after doing this parametric simulation analysis, the combination of the height as well as the dielectric constant of the available substrate in the market. Okay. So therefore, at this 5.77 gigahertz minus 28.50 return loss and 475 megahertz bandwidth, the epsilon r is 4.4. Okay, so that particular material is chosen. Okay, this is a simple example. Now I'll take you through 3 different types of reconfigurable antennas. The first one is the frequency reconfigurable antennas. I'll show you some examples, some research designs that we did, the work of my research scholar that I'm trying to explain to you here. Okay, so this is one design implemented by the research scholar here at NIT-Warangal called CPW fed E-shaped reconfigurable antenna with frequency diversity. So this is a frequency reconfigurable antenna and it is using E-shaped patch. This is my main radiating element and the feeding mechanism is actually CPW, Coplanar waveguide, as I've just explained to you some time back. Fine. So now these are the different dimensions. Okay. So various dimensions and various parameters that is shown, and the substrate used is low cost FR4. Okay, FR4 is the substrate material used, and typically in the market, if you want to buy FR4, 12 inch by 12 inch, that means 1 square feet area material costs you not more than 200 rupees. So with if you buy one FR4 substrate of 12 inch by 12 inch, 12 inch by 12 inch, that means 1 square feet area. Okay, and you can make at least you can make at least some 30 antennas using that board size. Small reconfigurable antennas or small microstrip antennas, whatever you are designing, because typically we'll be fabricating antennas with dimensions like this, 30 by 30 mm. 30 by 30 mm is actually 3 centimeter by 3 centimeter. Okay, so like that, if you buy 1 square feet FR4 board for about 200 to 300 rupees, you can make almost 20 to 30 antennas out of it. Okay, depending on what application that you are in. So that's why it's called low cost. Okay, yeah. So this is one example of a frequency reconfiguration antenna. So here, as you see in this diagram, there's a E-shaped patch. Okay, and there are two diodes here, S1 and S2. Okay, between the there are three elements of E. Okay, between the top one and the middle one, there is one diode. Okay, at a distance D from the edge. Okay, S1, it is called switch 1, and again we have another diode between the middle element and the bottom element of E shape, second switch. Okay, so now if you put two diodes here, it means we are shorting at a distance D. If you make S1 on, then the radiation characteristics of this particular E-shaped patch will change. Similarly, S1. Okay, so let us see now how this is behaving. These are the 4 modes. Because I'm using 2 switches, I'll get 2 raised to 2. That is equal to 4 combinations. Means switch S1 and S2 both are off. Both are off means what? There is no connection between the top element, middle element, and the bottom element of E shape. Okay, both are off means this is the thing. And in the second figure here, you see switch S1 is off between the top and middle, and switch S2 is on between the middle and the bottom. So therefore, these are shorted here. Okay, this is another mode. Similarly, third mode can be S1 on, S2 off. Fourth can be S1 and S2 both are on, as you see here. Okay, so if you can make this combination and try to get these characteristics of at what frequency this is radiating or resonant frequency, you will see the frequency will change when you operate in these 4 modes, and hence this can be called as a frequency reconfigurable antenna. Right? Yeah. So as you see here, in the performance results of antenna 1 means what? The S1 are off and S2 both are off actually. So it is resonating at 5.8 gigahertz. Okay. So this graph shows you by simulation. This is the graph, solid line, and when we made a measurement, okay, actual measurement we made and then measured the return loss, reflection coefficient, then we got that this dotted line. So therefore, this tells us the theory and measurement nearly agree. Okay, in the first mode, that means both switches are off, and this is a radiation pattern. Okay, diagram, and this is the photograph of the actual antenna that is fabricated, as you see here. So this is the actual photograph of the antenna that is fabricated. So as you see here, this is the antenna, E-shaped antenna, and CPW feed where SMA connector is soldered here. And from the scale you see, the size is about 30 millimeters, okay, by 35 millimeters roughly. That's why we always put a scale here to know exactly what are the dimensions. Okay. Of course, in this photograph the diodes are not seen, but I'll show you another photograph where they are seen. Okay, and okay. So in the simulation, what do? In the simulation, you treat practically you make the diodes on and off by using a DC bias line. Because it's a diode, we need 2 lines, positive and negative, from the battery or from the power supply. So when you forward bias the diode, it is on. When you reverse the diode, it is off. Okay. So practically you do that. But when you are doing simulation, you in the HFSS software or IE3D that you are going to learn, how do you actually model this switch? Okay. So we model this switch as a short circuit path to represent diode on, and don't put a short circuited path copper line there if you want to make a diode off. That's how we model them. Now this particular slide shows you that 4 different combinations with S1, S2 off, and S1 off and S2 on, and so on and so forth. So as you see here, with respect to the resonant frequency, with respect to the bandwidth and with respect to the bandwidth in gigahertz and bandwidth in percentage, and the S11, that is your return loss in dB. So mode 1, mode 2, mode 3, mode 4. Mode 1 means S1, S2 on, mode 2 means 1 off, 1 on, M3 means reverse, and M1 means both are on, both switches are on. So you see the frequency of resonance is now in mode 1 it is 5.8 gigahertz. In mode 2 there are two bands we got, as you see in this diagram. You see this is one resonant frequency and this is another one. One is at 5.0, other one is at 8.5 gigahertz. Okay, these are simulated and these are the measured results. Similarly, in mode 3 it is 5.57. In mode 4 it is 6.1, 8.76. So therefore, in this, these are the frequencies that we are getting when you operate in 4 different modes. Okay. Similarly, in all these 4 different modes, the bandwidth is also changing. Okay, and bandwidth percentage is shown here, and the return loss is shown here. Okay, so this is how we design the frequency recombinant antenna. A simple design that I have shown you. Based on this, actually, we can assess the performance with simulations as well as measurements, but they should nearly agree. That is important. Okay, then you can say that your antenna design is good. Okay, yeah. So this is one example, and similarly, this graph shows you measured VSWR and gain. Okay, gain is shown here. So in mode 1, the VSWR should be nearly 1 for the antenna to act as a very good radiating antenna, and gain is about 2.75 dBi. In mode 2, the VSWR is 1.33, 1.08 at 2 different frequencies, and the gain is 2.56. Mode 3, VSWR is 1. So therefore, VSWR should be nearly equal to 1. Okay, then we can say it has a very good radiating properties. Okay, and at least you should get a good gain for a given application. Okay, so this is one example that I have explained to you so far. These are the radiation patterns in all the 4 modes. Okay, so that is one example of a frequency reconfigurable antenna. This is another example of another reconfigurable antenna. This is called a reconfigurable slot antenna for diverse frequency wireless applications. Now in this case, it is actually called a T slot, T-shaped thing, and it has got 1, 2, 3 elements. Sorry, 4 elements, and there are 3 diodes in between, S1, S2, and S3. So since we have 3 diodes, I have 2 raised to 3, which is equal to 8. I can have 8 combinations or 8 configuration modes here. As you see here, see, case 1 is S1, S2, and S3, all are off. And case 8 is all are on. So therefore, I get 8 combinations now. So as you see in the parametric study here, in the parametric study, as you see here, when some of the parameters are changed with respect to this one, so we have to identify the frequency and the bandwidth and a good return loss. Now in this case, and in the W3 is one of the parameters. So W3 is actually here. That is actually the width of the individual segments of the T radiating patch. Okay, this is the radiating patch with 4 elements. W3 is actually each of them. So by varying the width, how the return loss changes, that is a parametric study that is shown in this graph. Okay, similarly, when you vary the thickness of the substrate T, how it changes. Okay, after this parametric study, we have to choose one of them. Okay, we have to choose one of them depending on the availability of your substrate in the market. Okay, so T is actually T is actually this one. As you see here, T is the thickness of the board, okay, of your substrate. So after this simulation, we have to choose appropriately which one is there. Now in this case, we have chosen T as 0.8 mm board because our interest is 5.61 gigahertz and minus 22.6 return loss, and then bandwidth is 2 gigahertz. So this is the thing. Now here it shows how the return loss varies in all the 8 combinations. Okay, so you have to see now out of all these 8 combinations, 8 different frequencies, which is suitable for your application. So remaining things we will not do. Okay, means let us say my interest is at my interest is 2.4 gigahertz roughly. then I will choose mode 1, case 1 only. If my interest is 6 gigahertz around, okay, I will choose case 1. So depending on that, we can choose. Okay, so these are the again graphs of different cases of how the measured and simulated results can be shown. So therefore, the solid line is simulated and the dotted line is the measured results that we have got. And this is the diagram of a radiation pattern. Different radiation patterns for different cases. This is case 1 and case 2. Okay, so it is giving me 8-shaped radiation pattern. So typically the radiation pattern of a dipole kind of a radiation pattern. Okay. Okay, so this is in case 1 and case 2. There are different cases anyway here. Case 1 and case 3 and case 4. And this is the overall comparison of all the 8 modes. As you see here, we are having from case 1 to case 8. Okay, because we are using 3 diodes here, and the antenna also I have shown you already that which we have fabricated at NIT-Warangal. So operating frequency. So the figures shown in the bracket and they are measured values, and these are simulated values. Okay, yeah. So as you see here, case 1 and case 2, 5.85, 5.7, 5.61. So and 5.34. So this whole case 1 to case 4 can be used for wireless LAN application, WLAN application, as you see here. And similarly, case 5, I have 4.85 gigahertz that is used in Wi-Fi IEEE 802.11 application. Okay, and case 6, okay, is a C-band application at 4.61, and case 7 at 3.99 is a S-band application, and case 8 at 3.07 gigahertz, it is a WiMAX IEEE 802.16 application, 802.16 application, and the corresponding VSWRs in all the 8 cases, corresponding bandwidths in percentage, and corresponding gains in dBi is they are also shown here, and the corresponding return loss. Okay. And return loss is also good, and VSWR is nearly 1, so therefore the antenna performance is also better. So this is another example that I wanted to discuss here under frequency reconfigurable antenna. Okay. So this is some comparison that we made with existing the literature. Okay. So this is our proposed antenna that I have shown you. One E-shaped I have shown you. One T-slot I have shown you so far. Number of switches in the first case we have used 2. In the second case we have used 3 switches, and these are the dimensions: 30 mm by 30 mm by thickness 1.6, 35 by 30 by thickness 0.8. Number of modes 4 here and 8 here. And these are the operating frequencies, and these are the bandwidths. And these are the research done by others. Okay, other researchers, and their boards are having this size. Okay, so we are trying to show here that the design by ours is nearly having we are trying to compare the complexity here, and we want to highlight the dimensions, saying that our antenna is compact compared to others antenna, okay, other researchers antenna, because dimensions are small. So though we have one exception here, 18.3 by 29 by 3, but as you see here, the thickness is more here. Okay, so it's bulky, it's not lightweight, and also the frequency is different for a different application, and gains, okay, are different. So such kind of a comparison can be made always with respect to what exists in the literature and what kind of a new thing that you design, and hence it may be accepted for publication in the research journals, that your work is when you compare your work with others, it is reasonable, and your parameters are better than the others, and hence your research is now accepted. Okay, so that's how we do always the research in this field. Yeah. So this is a summary of the 2 antennas that I have talked about so far. Okay, and now I'm showing you polarization reconfigured now, the second category, that how do we design, and some examples that what we did here at NIT I'm showing you. Okay, and as you see here, this is one example done by my research scholar. All these are actually done by my own research scholar that I am trying to explain here. Yeah, this work is done by Dr. Sulakshana. Currently she is working at Vardhaman Engineering College. Okay, after doing her PhD here, she worked in UK. She has done postdoc, and then after that, now she is working. So all the work that I'm presenting is the work done by her. Okay, so now this is the example of what is called a CPW fed rectangular reconfigurable patch antenna with switchable strips for polarization diversity. Okay, to change the polarization, how are you reconfiguring? One example that I'm showing you. Okay, so yeah, so as you see here, we have a rectangular patch here, and there are two small strips on left side and right side, and which are connected to the main rectangular patch by two switches. See, this is one switch, and this is another switch here, and the mechanism and the mechanism that we have here is a CPWD feeding mechanism. As you see here, this entire black thing around the edge is a ground plane, and this is the central feeding line. Okay, so this mechanism is called now CPW, Coplanar waveguide feeding mechanism, and these are the various parameters, different widths, different gaps, and various things. And dielectric constant is 4.4, and these are the various dimensions given on the left side. And the substrate is again FR4 only, low cost FR4, substrate that we have used here. Okay, so now this slide shows you different configuration. Case 1, that means both the switches are off. It is actually gives me linear polarization. Now this is case 2, where the left switch is on, right switch is off, which gives me left hand circular polarization for me. And this case 3, giving me right hand polarization, where the right side switch is on. And the fourth case, as you see here, it is actually gives me again linear polarization when both the switches are on. Okay, yeah. Okay, so yes. Now, as you see in this diagram, this shows me, this is the evidence. Okay, the case 2 is shown here. Now, case 2 is what actually in the previous slide, as I shown you. The previous slide, case 2 is actually left-hand circular polarization. Okay. Now, how do you know it is a left-hand circular polarization? So that is known by looking at this, current distribution. So this kind of current distribution plots can be obtained through your simulation software. Okay. So as you see here, in one cycle T0 to T4 to T by 2 to 3000 T4, one full cycle, as you see here, the current vector directions, you see how it is changing. Okay. So you should know the meaning of left-hand circular polarization and the meaning of right-hand circular polarization by knowing the Fleming's rule, Fleming's thumb rule, by which we will know how the the vector is changing either clockwise or anti-clockwise. As you see here, how the direction of the electric vector is changing from T0 to the full cycle. Okay, so from that we can conclude that it is a left-hand circular polarization. That is case 2. Okay, like that we can see the current distribution in all the cases, and then we can now conclude that by appropriately operating these two switches, we will get from linear to right-hand circular and right-hand circular to left-hand circular, and so on and so forth. This is an example of a polarization recombinant, and these are the results of this particular antenna that we have designed here. Now the first case is S1, S2 both are off, linear polarization. Okay, this is the photograph of the antenna. Okay, of course the diodes are not seen in this photograph. Practical photograph maybe I'll show you at the end. Okay, where with we have the bias wires connected to make the diodes on and off. And as you see from the scale here, dimensions are roughly 30 mm by 30 mm, 30 millimeter by 30 millimeter. And then here you see azimuth and elevation radiation patterns. And in this plot you will see simulated versus measured results. Okay, in linear polarization case. Okay, and similarly other cases. This is LHCP, where we have got two resonant frequencies here. Okay, where S1 is on and S2 is S1 is off, and antenna to S1 off, S2 on. Okay, maybe reverse case. This is 5.8 gigahertz. Okay, and this is at 4.5 gigahertz. So different combinations are shown to you. Again, this is both are on, both switches are on. Okay, again linear polarization at these two frequencies. Okay, so now this is the summary. Okay, in all the four modes, what frequencies that we have got, and how the measured how the measured and simulated are compared here, and what kind of bandwidth that you got, and what is the return loss like. Now we know from your basics of yesterday's session, maybe at minus 10 dB we draw a line here at minus 10 dB in the return loss graph, and then when it cuts this region at this place to this place, and that we take as the bandwidth, operating bandwidth of the antenna. Minus 10 dB is the reference for us from this image, so therefore reasonably that the antenna is operating. Okay, so there we actually measure the bandwidth from simulated as well as the experimental graphs. Okay, so similarly, since it is a circular polarization that we are talking about, left hand and right hand, there is another parameter called axial ratio that we must actually measure whenever you talk about circular polarization. So the axial ratio should be nearly as see from this group from this graph. Okay, ideally it should be 0, but you are getting 0.9, 0.3, 0.9 in mode 2 and mode 3. Mode 2 and mode 3 are actually you are declaring as a circular polarization. So therefore you should also measure axial ratio and then confirm that it is really a circular polarization. So as I told you, to confirm whether the antenna is radiating circularly polarized radiation or not, one is to check with the current distribution through simulation software, and the other one is you measure the axial ratio both practically and simulation and see that it is nearly 1. Okay, or near to between 0 and 1. Okay, then we can say that it is okay, giving you axial, it is giving you circular polarization. Okay, and these are the radiation patterns. Okay, measured radiation patterns of the antenna in all the combinations. Okay, that is one example. Now this is another example that I am showing you again here. Maybe I'll have to go a bit quick now because already 11:30 and my time is up to 12 o'clock anyway. So this is another example that I am showing you here. It is CPW PET, similar like previous case, but here the patch shape is circular instead of rectangular. That is only change. Okay, and with polarization diversity. Okay, only thing is we have changed shape from rectangular to circular. We did not do anything else. Okay, and again in this case, again 4 cases we have on the photograph of the antenna that you can see here, and again 4 different. We got left circular, right circular in 2 different modes, and all these are the results. Okay, now what we did in this thing, we are comparing with other researchers, okay, who also designed similar such antennas. So we tried to compare in what way our design is better than their design in terms of maybe dimension. Okay, as you see here, these dimensions are actually smaller compared to all the remaining people. Well, you see, for example, here it is 100 mm by 100 mm. Here it is 50 by 50 mm, 100 by 100. This 78 mm. So compared to all these references that I am showing here as an example, that compared to them, our design is much smaller, compact, and then number of switches we are using only 2, whereas all these people except with these 2, they are using more number of switches, so complexity is more. Okay, so whenever you do such design, you should be able to, and we are all teachers, and whenever we are doing research work, PhD, we should come out with such comparison table with respect to existing literature and show that your performance is better than others, so that your research is accepted for publication. Fine, that way. So this is one another part, and this is a summary of the 2 antennas that I have talked about. Now the third one is actually pattern reconfigurable that we designed here. So this is one example of a CPW fed pattern reconfigurable antenna with multi-port excitation. Okay, unlike previous cases, here we have got 4 ports, but we will be using 1 port at a time. Okay, to get the pattern reconfigurability. But of course, here we are not using any switches for the time being in this design. We are only switching the feed. We are only switching the feed location. Okay, no switches are used here. Again, we have used FR4, and then you see the dimensions are, antenna dimensions are 14 mm by 13 mm. Okay, 14 mm by 13 mm, that is so small, almost it fits on your thumb. So small it is, and yeah, and we are only switching the port here. We are not using any switches, but it is now can be called as a pattern reconfigurable with multi-port excitation. As I again told you, this is a parametric study that we do in simulation, but varying different heights of the substrate, and we choose the optimum one which is available in the market. Okay, and now this slide shows you the actual antenna photograph that we did here, and then the feed line that is shown here. Now this port is being used to feed the energy, and all the remaining 3 ports are terminated by matched loads. Okay, and and this is the performance graph that we are showing here. Right now it is fed at port 1, and here that means it is fed here, and here it is fed at port 2, and here it is fed at port 3, and here is at port 4. Okay, so we are only changing the feed location. Okay, and then by all these 4 ports we have got nearly same operating frequency. This must be, see, because it is a pattern reconfigurable antenna, only pattern should change its direction, but the frequency should not change. That is important. Okay, so therefore now the frequency has to be same. Okay, the frequency has to be same, and it should not actually change. That is important. Only pattern should change. Okay, I'll show you the patterns here. Yeah, so as you see these diagrams now, when you feed at port 1, the pattern is like this. When you feed at port 2, the pattern has reversed now. When you feed at port 3, it's a different orientation, and at port 4, it's a different orientation again. Okay, so this is actually called the pattern reconfigurable antenna. Okay, and this is the photograph of the antenna, and the dimensions are, as I showed you here, 14 mm by 13 mm overall antenna. So small it is. And let me tell you, so far this is the smallest ever designed in the literature. Okay, there is no antenna existing in the literature so far of this particular smaller dimension for pattern reconfigurability. Okay, this is accepted in one of the best journals, that the smallest available in the design so far for pattern reconfigurability. Okay, so when you are actually trying to do a multi-port excitation, you also should calculate what is called envelope correlation coefficient, so that the coupling from one port to another port is not much. Okay, that we do by calculating what is called a parameter called rho, called envelope correlation coefficient. Okay, that should be very, very small. Okay, when you are actually trying to use multi-port excitation. Okay, so this graph shows you the transmission coefficient in dB, and correlation coefficient is shown in this graph. Okay, which is very, very small. Okay, this has to be verified both theoretically and practically to see that. Okay, fine. Again, this is the comparison of our design, okay, with others in the literature. Okay, and see the dimensions and see our dimension. Okay, this is so compact. And then operating frequency different. Maybe we designed for K-band and others have designed for UWB and Wi-Fi and other frequencies. And the bandwidth, better bandwidths we got. Okay, so this is example of one such thing called pattern reconfigurable antenna. Okay, yeah. So then the last case that I'll quickly explain to you is now design of compound reconfigurable. That means combination of previous frequency, polarization, and pattern. Combination of these things we should be able to take. Okay, so this also we did one such design. I'll show you now, called compound reconfigurable. So this is the antenna that we did for compound reconfigurability. Now, as you see here, this is the overall antenna picture. We have got 4 rectangular patches. They are interconnected by 3 switches, S1, S2, and S3. Okay, so we have used same FR4 substrate, 2.1 mm thickness, and dielectric constant 4.4. And the dimension again very compact it is. It's only 16 mm by 16 mm. So it can be used for all applications like smartphones and all the small electronic gadgets with the different reconfigurability that we can do. So this slide is showing you all the different modes: mode 1, mode 2, mode 3, and mode 4 by respectively operating the. Even though we have 3 switches, I get 8 different modes, but we have taken only the modes which are useful. Other modes we have rejected. Okay. So for example, in this mode 1 and mode 2, frequency diversity mode of operation that we are getting. Okay, mode 1, mode 2 means what? In this. So therefore here S1, S2, S3. S3 is on, but here S1, S2 are on. So in these two combinations, I'm getting frequency diversity. Whereas in mode 3 and mode 4, okay, now S1 and S3 are on here. Here, S3 and S2 are on here. Here we are getting polarization and pattern, both we are getting here. Okay, combination of polarization and pattern, both we are getting. See, reconfigurable doesn't, the compound reconfigurable antenna doesn't mean that all three we should get in the same design. Frequency, polarization, and pattern. But we can get any two. Okay, if you can get all the three, that is fantastic. But so far we could not do that. We could get only this in our research, but we are trying to do better designs. Okay, so yeah. Again, as I told you here, whenever you talk about circular polarization, again through current vector rotation and current distribution, we should confirm whether it is LHCP or right-hand circular polarization. Okay, yeah. And then these are the results of simulation and measured that how do you get for the antenna. Antenna photograph is shown here for you. Such as small antenna, it's only 16 mm by 16 mm design. Okay, so just small antenna here. And then you can see this is a frequency diversity case, okay, where frequency is changing from this to this, and this is actually polarization and pattern diversity case. Now as you see, S1 S3 on, S2 S3 on. Okay, you see, whenever we talk about pattern diversity, polarization and pattern, the central frequency should be same, which is maintained here, as you can see here. But whereas here, when you talk about frequency reconfigurability, the frequency can change. Okay, frequency diversity, but here the frequency should not change, only polarization and pattern should change. Okay, now this is the three-dimensional picture of a simulation radiation pattern, where you can see the pattern and these things are changing. Okay, and now as you see in this diagram, for the left hand linear polarization, okay, frequency reconfigurability, linear polarization, you can see the things, and mode 1, and in mode 2 again linear polarization. As you can see from here, the frequency change from here to here, and then in mode 3 right hand circular polarization, these are the frequencies, and mode 4 is left hand circular polarization, and these are the measured and simulated things compared, saying that both agree, so that the antenna performance is better. And again, as I said, whenever we talk about circular polarization, we should also be aware of what kind of gain you are getting, and importantly, what is axial ratio. So axial ratio is nearly 0. So therefore, as you see here, between 0 to 1 that we have in dB anyway. So therefore, it is confirmed that you have the circular polarization, and this is the comparison. Okay. So I'm showing you the comparison that we have for existing with others. See, mode 1 and mode 2 frequency diversity, and mode 3 and mode 4 are polarization and pattern diversity examples. And as you see here, the values of operating frequency, then return loss, okay, then frequency, frequency band in which they are operating, then measured gain, and what is the bandwidth like, and bandwidth in percentage, then VSWR that we are getting here, and then axial ratio bandwidth, axial ratio value, and what kind of polarization that you are getting, and what is the application. Okay, so this is how we should be able to project the results, and for which application that you have designed, whether it is conforming to that particular design or not. Okay, yeah, and these are the photographs, various antenna that I have talked about so far, and as I told you, and this is the this is called the anechoic chamber, where we have to do all the radiation pattern measurement that I have shown you. We have to do in a special facility called anechoic chamber, so that the reflections from the surroundings are avoided, and hence the radiation characteristics can be measured with good accuracy. Okay, so that is the facility that we have used. Of course, here we don't have anechoic chamber here at our institute, but we took the antennas to defense labs, in which we have contacts in Hyderabad, and there actually we have measured the radiation patterns. Okay, so this is the conclusion of my talk so far, right, of two different, antennas, that three different categories of antennas, and their reconfigurability mechanism is actually shown to you. Okay. Yeah. So that's all. Okay. Thank you for your patience. This now it's almost 11:50 that I'm concluding my talk. I thought I'll spend a little more time on different feeding mechanisms if time permits. But anyway, it's up to you. Now I leave another 10 minutes for maybe small questions. Yeah.
Sir,
Sir, if you
sir, sir,
Yes.
sir, we have a small doubt, sir. Sir,
Please.
while inserting pin diodes, what are the measurement criteria for the inductor, capacitor, and filter? Inductor, capacitor, and resistor values, sir, for on
Yes.
and off conditions.
Yes. Yes. Actually, whenever we use pin diodes, we need to design a biasing network. Okay. So the biasing network, though I am not shown in my slides, the biasing network will have the inductors, capacitors to be chosen. So we need to have a biasing network separately on a different board, or if possible, you can also mount on the same boards. So what we did in our research, we didn't include the bias network on the antenna board, but we designed it on a separate board. Okay, and from there we have used a very short length of wires to connect to the switch. Okay, so therefore the values of inductors and capacitors that you need, or you need to choose, because they are all very small tiny elements, almost of the dimensions of about 1 mm, 1 square mm rather, which are to be soldered on the bias network board. Very carefully we have to do that because they are very small tiny elements with surface mounting device technique we have to use with very, very sharp soldering iron with a very low temperature. Otherwise, these devices get spoiled. Okay. So now coming to your question of how do we choose the L value and C value for the biasing network. So we should see that depending on what is the dimension of the no, first of all you should get the equivalent circuit of the system. Okay. So I have unmuted my mic, it got muted. So therefore, what you have to do, we have to first of all work with the equivalent circuit of the diode in on condition and in off condition. Okay. So from the literature or from the data sheet of the diodes that you have picked up, okay, note down the values of on resistance and off resistance of the diode, and we get the equivalent circuit, equivalent model of the diode. Okay, and then your bias network should be in such a way that the inductors, because we are using a DC biasing network and which is now being connected to board which is operating at gigahertz. So therefore the inductor should give you DC continuity. At the same time, you should have very high impedance as far as AC is concerned. So that means that the DC current should not go on to the patch antenna. That's where actually we use inductor. And similarly, we use a capacitor so that high frequency signal can flow between the elements of patch antenna. At the same time, the DC voltage should not, be transferred onto the patch elements. So the capacitor blocks DC and allows high frequency AC, and the inductor, gives a continuity for DC to flow and also blocks high frequency AC. Now for choosing the values of C and the inductor L, so you should get the equivalent circuit. Okay, and from that, you have to work out. But the practice and experience shows that for a given band of operation that we are using, right? So these capacitors and inductors are available ready-made. Only thing is see their band of frequencies from the data sheet. So those you can use directly. You don't have to really, you don't need really to do a great exercise in choosing the value of capacitors and inductors, okay, which are available generally in market. Only see the data sheet and see the operating frequency band. That's all. And similarly, whenever you use the SMA connector also you have to choose appropriate to the band of frequency of your interest from the data sheet. Okay. Now see that the band of operating band usually generally we take DC to 18 gigahertz for normal applications. You see that the operating bands of SMA connector and the diode, the capacitor inductors match. So it will not actually create a great mismatch when you are choosing the capacitors and inductors. Things which are available in the market can be chosen generally because they are part of only your DC biasing circuit.
Okay, sir. Thank you, sir.
Yeah.
Thanks a lot, sir.
Yeah. So if any doubt you have, you can always write to me. So my mail ID is anjan@nitw.ac.in. Okay. So I'll try to answer your query. There's no issue at all.
Thank you, sir.
Yeah.
Hello, sir.
Yeah. Please.
Hello, sir. Sir, another one question, sir. There.
Yeah.
Sir, how to read the surface current?
How to read?
The surface current.
Even I am having the same question as you have mentioned. If you wanted to identify the polarization pattern, is it left circular polarization, right hand circular polarization? So from the current distribution, how can we identify that?
That's what. I'll just go back to that slide where I've shown that. Then you'll be able to understand. For example, I'll show you. So you have to see from T0. I'll show you that. I'll just, for example, see this here. Okay. Now this is showing LHCP. It means you see now you see the arrow current vectors here. Okay. Now from T0 to T4, you see the arrows are actually at T0. You see these arrows are straight. Okay. At T/4, you see arrows are inclined. At T/2, they are also inclined. At 3T/4 also inclined, but in different direction. So therefore, as you see here, from D0 to 3T/4, the arrows are actually rotating in the anti-clockwise direction. Okay. The arrows are rotating in the anti-clockwise direction. Right. So anti-clockwise direction is actually from the rule, it is left-hand circular polarization. Okay. But from T0 to 3T/4, that means full cycle is covered. But whereas if you see the direction of arrows moving in the clockwise direction, okay, then we can treat it as a right-hand circular polarization. So that's how we should identify if it is LHCP or LHCP. This is based on your thumb rule. Okay. Like you see, for example, if I hold my thumb here, if my finger is pointing the power flow direction. Okay. So the direction in which my fingers wrap, okay, tells me whether it is a LHCP or RSCP. Okay. Go and coming out of thing or going in. For example, if I hold like this, okay, or if I hold like this. So depending on that, it is a clockwise or anti-clockwise, LCP and RSCP are noted.
Sir, whether we have to identify the current direction, from where we have to identify, on the whole surface or on the only patch?
No, on the patch only. As you see here, T/4, you see here, T0, it is like this. At T4, they are wanted 45 degrees from down like this. Okay. So the vector is now moving in the anti-clockwise. Okay. That means wherever there is a active radiation, there we have to see. Okay. The active radiation is happening here. Okay. Where? At the switch, which is closed. And at T/2, as you see here, that again direction has changed. And at T/4, direction is now completely on the other way. So if you see T/4 and 3T/4, as you see here, the arrows are reverse. See here, 3/4, if you see the arrow here, and 3/4. So that means it is actually moving in anti-clockwise direction. Okay. So that's how actually.
Hello, sir.
Hello, sir.
Sir, one more doubt is there.
Please.
Sir, actually, one person is designing some circular polarized antenna. He got that axial ratio between 2.9 to 4 gigahertz. For impedance bandwidth between 2.9 to 4 gigahertz and axial ratio between 2.7 to 4.3. Whether it is correct or not is asking.
Okay. Can you please repeat the question again? Though I understood.
Sir, one person is designing that circular polarized antenna.
Okay.
That impedance bandwidth from 2.9 to 4 gigahertz.
Impedance bandwidth. Okay.
2.9 to 4 and axial ratio between 2.7 to 4.3. Whether it is correct or not, he is asking.
So axial ratio is very high actually in this case. Impedance bandwidth 2.9 to 4 is actually 2.9. Let's say if you take nearly 3 to 4 gigahertz is about 1 gigahertz bandwidth they are getting. Okay. 1 gigahertz bandwidth we are getting. Nearly 1.1 gigahertz bandwidth we are getting. And axial ratio you are saying 2.7 to. So therefore now axial ratio is high. I don't think it's a pure circular polarization. Because for a pure circular polarization, the axial ratio between nearly, between 0 to 1 for a pure circular polarization. It's high actually. That means the polarization purity for circular polarization is not great in the design.
Hello, sir.
Sir,
Yeah.
Sir, one more question. What are the best techniques to achieve impedance matching, sir? Best techniques to achieve impedance matching.
Better techniques to achieve impedance matching. Okay.
Yes, sir.
Yeah. So I'll just maybe another thing here. Can you see my screen, please?
Yes, sir.
Yes, sir.
Yeah. I'll just show you. You see here. For impedance matching, one is design, the other one is, as you see, actually this is what I thought I'll cover if there is time. For better impedance matching, there are, different techniques. I'll show you, see, for example, here, okay. I'll just show you I have some comparison of all these different feeding methods. Anyway, I've already shown you earlier. I think I have here one more. See, this is about improving bandwidth. Yes, I already shown you earlier. See, impedance matching, as you talked about, for patch antennas.
Sir, your screen is not visible, sir.
Oh, is it?
Sir, screen visible, sir. Screen visible, sir.
Visible, na? Yeah.
Yes, sir. Yes.
Okay. So you see here, if you see impedance matching or improving impedance, these four are suitable: microstrip feeding, coaxial feeding, proximity or aperture coupling. Okay. So to have a better impedance matching between the radiating element and your and your source, better we use one of these four methods. Use microstrip feeding, coaxial or proximity or aperture. Okay, which gives you good impedance match. But however, if you are using other than these things, then we have to appropriately design. For example, I'll show you a case where you see here. Okay. For example, take this case. Okay. Now in this case, it is using a quarter wave transmission as a feeding method. So now in this case, between the patch and the feeding element, I need to have another, lambda by 4 line here to have a proper impedance matching at the source and at the radiating patch. I need to design this another lambda by 4 in extra section in between for proper impedance matching here. Patch antenna with a quarter wave wavelength matching section is additionally needed. Okay. So where your impedance matching can be done by this particular equation using quarter wave transformer line thing. Whereas if you want to have a better matching, if your impedance matching is of main criteria, then don't use this this kind of feeding mechanism. So better use the feeding mechanism which I have just suggested. Either use microstrip line or use coaxial or use as I shown in the previous case. Okay. So to have a better impedance matching, as I have shown in my previous slide, use one of those 4 feeding mechanisms. Okay, that will solve your issue. Okay. This
sir,
one.
Hello, sir.
Out of these 4,
Hello?
sir, which technique? What are the better techniques, sir, out of these 4 to achieve impedance matching? Which technique? Which technique is suitable? Better advancement of the best technique
So
to achieve the target 50 ohms impedance line.
Yes. Out of this, see again, as I told you, it is coupled with other things. See, if you want of easy feeding method, then microstrip and coaxial are better. Okay. If you are concentrating only on impedance matching, but now, but if you also want other thing, like see, for example, that's the reason why I showed you this one. Okay. Now you see aperture feed. Now in the previous thing, aperture is giving good impedance, but you also see what are the other advantages of aperture. You see here, return loss is less. So therefore, now if you want to have better return loss, okay, and better impedance matching, then aperture. Hello, can you hear, please?
Yes.
Am I audible?
Yes, sir. Yes, sir. Audible, sir.
Yeah. So if you want better impedance matching and better return loss, then aperture is not suitable for you because aperture is giving me less return loss. Okay. And also polarization purity is excellent in aperture. So if at all you want excellent polarization purity and better impedance matching, in that case go for aperture. Okay. If you want, so that's the reason why I'm showing you this graph. And also you get very good bandwidth when you go for aperture. So depending on these combination of these things, you should be choosing one of these 4. Like you asked, the question is which one is better out of these 4 for impedance matching. But all these 4 are again, are governed by these parameters. Okay. So accordingly, you have to design.
Thank you, sir.
Hello, sir.
Yeah.
Hello, sir. I'm having 2 questions. Can you please answer them?
Yeah, please.
Sir, my first question is, what is the difference between frequency reconfigurable antenna and multiband antenna? And the second question is, as you have mentioned, if we wanted to, in reconfigurable antenna, if we wanted to put up, let's say, some switching elements like pin diode or PN junction diode. So while doing it on hardware, we may use them, but on the software, are they these components are directly available, or do we need to just shorting them?
Okay, fine. So the first question is difference between multiband and reconfigurable frequency reconfigurable antenna. Okay, if you see the English meaning, just English meaning, it is the same, but technically they are different. Okay, so when you say generally English meaning, as I told you, generic meaning of English is same. Whether you call it reconfigurable, see, multiband means what? The antenna is operating in 3 different frequencies. Okay, so reconfigurable antenna is also operating 3 or 4 different frequencies. So English meaning wise, both can be called as multiband because they are operating in multiple bands. But technically, the difference is that when you say reconfigurable, all the 3 bands that it is operating are not simultaneously achievable. It operates in one band, then it can be switched to another band, and then it can be switched to another band. By only switching at any given time, it operates only in one band. Okay, that is the reconfigurability frequency reconfigurable antenna. But when you say multi-band antenna, generally you can design an antenna which has 3 frequencies operation at the same time possible. Okay. For example, one of the designs I have shown you there are 2 resonant frequencies. Okay, and there are 3 resonant frequencies, and in some case also we can get 4 resonant frequencies in the return loss plot. Okay, that is called a multi-band antenna, where all the frequencies are simultaneously either radiated or received by that particular antenna. Fine, that is called a real multi-band antenna. But only precaution or design mistake is that how do you isolate these frequencies when it is simultaneously transmitting or receiving? Okay, so there should be enough enough gap between these different bands. Otherwise there will be a kind of a mode mixing and other issues when the antenna is simultaneously transmitting or simultaneously receiving these frequencies. Okay, that is called multi-band, means all the frequencies are simultaneously transmitted or simultaneously received.
Got it, sir. Got it.
Yeah. And the second,
sir, we feel very much happy with you, sir, Professor Anjan, sir. Yeah. Sir,
thank you so much.
We are very happy, almost satisfied, sir. If you spare PPT or recorded version, we feel very, very proud from you, sir.
Yeah, whatever I have projected now, I'll share it on the mail ID of Samiran, which I have now currently with me. I'll share them, no problem.
Oh, okay, sir. Thank you.
Yeah.
Second question, sir.
Yeah, the second question about the diodes. Yeah. So the diodes actually, when you are modeling the diodes in the software, okay. So, I mean, many researchers that we have seen, and we have gone through several papers, many of them, nearly 99% of the researchers in the reconfigure field, they are using only very small shorting line in the simulation software as an equivalent model for a switch. Okay, because the values of resistances, if you see the equivalent values of the diode in the data sheet, they are so small, which are nearly same to a small shorting line that we model. Okay, so we have not seen any deviation, lot of deviation between a shorting line. But however, in the software, the diodes that are, some packages use diodes as well, but the difficulty comes in whether it is actually modeling properly or not. Okay, right. So our experience shows that it is better always you model with a small shorting line rather than trying to use, because the reason is that it's an active element. Switch is an active element. When you put on that, accordingly, biasing network also you have to design and do it properly. So therefore, the simulation software, it may actually take in a different way, or many times, what our observation is, when you change the even when you change the pin diodes of very near same characteristics, but we have seen there are a lot of change in the return loss and the radiation characteristics. Okay, so I suggest is, you can always model as a very short path when you model the switch in the software, rather than taking a diode in the place.
Sir, but how can we differentiate between if we use, suppose, this shorting path, small shorting path? So how can we differentiate, like, is it pin diode or PN junction diode? Because that thing is not available there.
No. See, only either we make the shorting path to show the shorting path to say that diode is on, or remove the shorting path to say the diode is off. Because the reason what I'm trying to tell you, the reason why I'm telling you, whatever experimentation that we have done for the dimension of shorting line that we have used. Okay, dimension means what? The length and width of the copper line as a shorting path, and calculate what are its equivalent resistance, and compare that equivalent resistance diode that we are choosing. Okay, so that particular diode whose on resistance is nearly equal to the resistance of the short copper line that you are trying to mimic as a diode on condition. Okay, and for diode
So
off, there is
do
no
we need to
problem
use,
because
sir?
Yeah.
Sir, do we need to use copper material there or something else for shorting?
Copper only.
Copper.
Sorry, sir, but if we use that one, it can function as another stub and radiation characteristics will be changed, no, sir?
I mean, you use a small line, you are saying?
Sir, if we use that short in the patch, then that small short line can function as another stub and the antenna radiation characteristics may be changed, no, sir?
So that is why you have to do what is called parametric by changing shorting line.
Sorry, sir, your voice is not audible.
There is a lot of noise, sir.
I don't know from where it is. On the other side, people have to keep their mics.
Please mute mic.
Okay, see, my mic is getting frequently muted. I don't know. And again, now I just unmuted my mic. Okay. Okay. So to ensure that matching, we have to actually change the position of the shorting copper line and then do a parametric study. Whenever you get good return loss, that position you have to decide for keeping a shorting line there. So when you get a return loss, a good match. You should decide the position of the shorting line by doing a parametric study with respect to the other wherever you are keeping the diode now. Okay, we have to slightly vary the position. But anyway, that is only one way of doing that. Otherwise, you can try picking up a diode from the list of diodes supported in the software and then try experimenting with them. So the software now will take its equivalent model at that position and then try to get the desired parameters or the radiation, the field patterns. Okay.
Thank you, sir.
Sir, one more doubt, sir.
Yeah, please.
Sir, assume that I'm doing frequency reconfigurable antenna. Assume that I'm using only one pin diode. During on condition, it resonates one frequency. During off condition, it resonates another frequency. What is my question here? It is each frequency it should be at 50 ohms impedance, sir.
Yeah, of course.
So yes, each output frequency it should be at 50 ohms.
Yes. Yes, should be 50 ohms. So you can cross check from the Smith chart if your software supports, or you should see from the return loss. So you do a parametric study to start with, and parametric study you can vary various other other things like width and length of other elements, keeping the position of the switch, and then see wherever you get very, very low return loss, that position you can take. Only with parametric study we can do that.
Thank you, sir. Thank you for your explanation. And we had gained, and all that the participants are gained lots of valuable talk, valuable material from your talk. From the reconfigurable antenna for that circular polarization, right hand circular polarization, left hand circular polarization. Thank you once again, Anjaneyulu sir, for taking our invitation and giving me that such type of good presentation to us, that we are all understand whatever and we are gain some knowledge. And once again, thanks to our management, VMTW management, Rataya sir and Shravan sir, as a Vignan group of chairman and CEO sir. Also thankful to our HOD, Mr. Vijay Kumar Arkude sir, and also for that all that the department faculty for which we are get that much of good attendance, and we are completed such session in a very good way. Thank you once again. Thank you all the participants. And once again, every day not require that feedback link. Feedback link we are share on the Saturday evening, and there will be every day rating you are given that. So no require every day that feedback link. Feedback link are given on that the last day, the Saturday night. And again today there will be again no session. Again tomorrow there will be session start from 10 a.m. Thank you all the participants.
Thank you so much.
Sir,
Thank you.
it's for organizer. Sir,
Yes.
Is it possible to send this recorded session, sir?
Yes, sir. Every day I will send that the recorded session with that PPT to that the group. Whatever WhatsApp group and Telegram group are there, we can share that in that the group.
Thank you.
Okay, thank you so much. Now I'm signing off. Bye, everyone. Yeah.